Good day, students. Today we want to consider a topic titled entropy change. We want to solve problems that involve entropy change. But before then, we must know what entropy is all about. Entropy is the measure of the degree of randomness or disorderliness in a system. Now you are given chemical reaction as written above. 2 moles of hydrogen sulphide reacting with 1 mole of sulfur oxide at the reactant side to give us 2 mole of water, which is liquid, and 3 moles of sulfur, which is solid. Now let's know whether the equation is balanced before we proceed. We have 4 atoms of hydrogen, 2 times 2, 4. You multiply it, and you have 4 here also. We have at the reactant side, we have these 2 is affecting this sulfur, 2 sulfur here plus 1 sulfur, 3. And we're having 3 sulfur here. Okay, let's go to the oxygen. Oxygen is 2, oxygen is 2 at the side. And we have to predict theoretically whether the reactions will take place with increase or decrease in entropy. How do you know whether it is a decrease or increase in entropy? This is the way you will know. When you are solving it, always consider and put into consideration those ones that are written in gases and those are written in liquid and solid. When those are written in gaseous form, there is a bracket that is being signified as gases. They have more reaction to be put into consideration. But those that are written in liquid and solid will be neglected because of the nature of the attractive forces in their molecules. Because in molecules of liquid and solid, we have a strong attractive forces that hold the molecules of the substance together. But when you talk about the gases, the gaseous substances, which is this hydrogen sulfide and sulfur oxide, they have random motions taking place more than that of solid and liquid. That's why you neglect those of the solid and the liquid when you are considering equation like this. Okay, how to predict is that we have 3 moles, the number of moles of substance of the gaseous substance at the reactant side is 3. Let's write it down. For the first part, the number, because we have to get it theoretically, the number of moles of the gaseous reactant is 3, while that of the product, the gaseous product is 0. Why do you say 0? Because none of them has gas. None of them has gas in the product, but in the reactant we have 2 plus 1. There's 1 at the back of sulfur oxide. When 1 is not written, nothing is written, it's 1. Take it as 1. 2 plus 1, that's 3. Is that okay? There is therefore an increase in the degree, a decrease, therefore a decrease in the degree of randomness at the products at the gaseous products side. Is the gaseous product side. Okay. Hence, there is a decrease in entropy. A decrease in entropy, which is like a decrease in the randomness at the product side. Is that okay? That one solve for the first one. Let's predict the second one. Let's call this one A1. Let's go to A2. In A2, when you look at it very well, you will notice that this ethane. We have 1 mole of ethane plus 7/2 of the oxygen at the reactant side to give us 2 moles of the carbon dioxide and 3 moles of the water. Consider that they are all gases. At the reactant side, they are all gases. The ethane is a gas at this point. Now let's know at the reactant side the number of moles that we have at the reactant side. Reaction A2 we have 1 at the products at the reactant side. Considering the reactants gases or gaseous reactants, we have number of moles is as follows. When you have that, you have 1 plus, there's 1 here, plus 7/2, this over 1, LCM is 2, 1 in 2, that's 2 times 1, 2, plus 2 into 1, 1 times 7, 7, 2 plus 7, that's 9/2, which is 4.5 moles. 5 moles. Now considering A2 also, let's say A2 in reaction A2, considering gaseous products. When you consider these gaseous products, you are having the number of moles. Is 2 plus 3. They are both gases. 2 plus 3 equals to 5 moles. Consider there's an increase in the number of moles. That means that there will be an increase in the entropy at the product side. Is that okay? We have to predict theoretically whether the reaction will will take place in increase or decrease entropy. The first one, that will decrease in entropy because we have 0 moles at the gaseous product, no gases. On the second part, there's an increase from 4.5 to 5. Is that okay? Let's now say, since the number of moles of the gaseous product is greater than the reactant or gaseous reactant, than the gaseous reactant. Number of moles in the gaseous product is greater than gaseous reactant. There is increase in entropy. There's increase in entropy at the gaseous products. See, the number of moles of the gaseous product is greater than the gaseous reactant. There's increase in entropy at the gaseous product. Is that okay? Okay, that's it. That's that. And let's go to the second part of the question. We have to confirm it. You want to use, we have to confirm your prediction in A by calculations. Okay, if you get negative sign, that means that in the first one, if you get the negative sign, it's telling us that there is a decrease, which is confirming what we have here, decrease in entropy. Now let's do the second part. B, we want to confirm. Now, since we want to do that, you first write the equation and write their entropy under it. So in each, where you have 2, you multiply by 2. Where you have 1, you leave it like that. Now let's now have 2H2S gaseous, let's call it B1, plus SO2 gaseous to give us 2H2O liquid plus 3S solid. Now, since we have it like this, we now have 2 open bracket. What's H2S? Hydrogen sulfide, we have the entropy of 205.6. For the second one, SO2, sulfur oxide, 248.5 to give us 2 of water, which is our water is 69.9. Sulfur, we have 31.9. And don't forget that we have the formula which says change in entropy equals summation of the change, summation of all the entropy at the product side minus summation of the entropy at the reactant side. And let's do that of the product first. Summation of the entropy at the product equals, let's see the product, this is the product. You have 2 into 69.9 plus 3 into 31.9. We are considering the product first. Now when you do that, what you have in the calculation, when you press your calculator, you have 139.8 plus 95.7. When you add it, you have summation of the entropy at the product side will be equals to 235.5 joules per Kelvin. Okay, now let's get that of the reactant side. Now let's see that of the reactant side, summation of the entropy at the reactant side. We are having 2 into 205.6 plus 248.5. When you press your calculator, when you multiply it, you have 411.2 plus 248.5. When you add them together, you have 659.7 joule per Kelvin. Now let's get the subtraction now. Change in entropy, which is summation of the product, summation of the entropy at the product minus summation of the entropy at the reactant side. We have that of the product to be 235.5 minus the reactant 659.7 joules per Kelvin. Now the entropy change, when you do your subtraction, you're having minus 424 minus 424.2 joules per Kelvin. Okay, you can see that the entropy change is negative. Due to this, there is decrease in the total entropy. A decrease in the total entropy. Okay. Of the product, since it's less, entropy change is negative. Due to this, there is decrease in the total entropy of the product. Okay, it's saying that total entropy of the product is less than that of the reactant. Okay, it implies, let's just say it implies that there is, let's put implies, it implies that there is decrease in the total entropy of the product, since it's less than that of the reactant. Is that okay? That there is decrease in the total entropy of the products compared to that of the reactants. Let's put it like that. The entropy is negative. Entropy change is negative. It implies that there is decrease in the total entropy of the product compared to that of the reactants. Now let's see the second part. That's B2. In B2, we are having write it out first. C2H6 gas plus 7/2 oxygen gas to give us 2CO2 gas plus 3H2O gas. Same thing, we are applying the same formula. Change in entropy equals summation of the entropy at the product and a summation of the entropy at the reactant. Let's get the product, the entropy at the product. Summation of the entropy at the product equals the product side. Let's put it under so that it will be very easy for us. Let's first of all put the value under each compound or each element. As under ethane, what do you have? You have 229.3. Under oxygen, you have 7/2 times. What is the oxygen? The molecule, oxygen molecule, 205. Go for 2 of CO2, 213.6, and 3 of these 3 of water, 188.7. 188.7. Now from here you can now write the formula. A change in entropy equals the summation of the entropy at the product and a summation of the entropy at the reactant. Let's look for the summation of the entropy at the product first. At the product, you come here, write it out. 2 is the product side. 2 into 213.6 plus 3 into 188.7 equals to, when you multiply that, you're having 427.2 plus 566.1, which is equals to 993.3 joules per Kelvin. Okay, now let's get that of the reactant. Summation of the entropy at the reactant, which is equals to 229.3 plus 7 times 205 divided by 2. When you do that, let's first divide this. 7 divided by 2, that's 3.5 times 205. You have 229.3. When you multiply this in body mass, you have to do in body mass. multiplication before addition. That's why we have to multiply first. When you multiply this, you have a 717.5, which is equals to, when you add the m together, you're having 946.8 joules per Kelvin. Okay, now let's get the subtraction. We now be summation of the product, or the entropy at the product, minus summation of the entropy at the reactant, which is equals to, the product is 993.3 minus reactant 946.8. okay, when you do that, change in entropy will now be equals to, when you do a subtraction, you will have 46.5 joules per Kelvin. Now from here, now you can now say the entropy. Okay, let's say the entropy change for the reaction, so that we know for the reaction. It's an additional statement for the reaction. The entropy change for the reaction is negative. Okay. Now the entropy change here, the entropy change for the reaction is positive. In this case, it implies that there is decrease. The fact that there is increase now, because it's positive. Here, because it's negative, it said there is decrease in the total entropy of the product. Now it implies that there is increase in the entropy change, at the product compared to the reactants. There's an increase. Okay, the entropy change for the reactant is positive. It implies that there is increase in the entropy change at the product, so it is positive at the product compared to the reactants side. Okay, and that's why we can see that it agrees with our prediction. When we are doing the first calculation, we said decrease because the ratio of the moles is 3 to 0. Since 3 to 0, we said it decreases. That's why when we got the calculation, it was negative in the first calculation, and in the second calculation, it is positive. And we said this one, it increases the moles. We have 4.5 and we have 5 here at the product, and that means that for reactant is 4.5, and the product is 5 moles. 4.5 moles at the reactant, 5 moles at the product. And when we got the calculation, it was positive. That means that it agrees. Okay. The confirmation of the calculation shows the calculation confirm the prediction above. in A. The calculator confirms the prediction above in A, which is the theoretical prediction. This is the end of our class. Please subscribe to my channel so that you can have access to the latest video. Have a wonderful day.